And welcome back to another lecture of probability and measure. Today we get to talk about inequality. That is, inequalities in LP spaces, because when you're working with LP spaces, you need a lot of inequalities to get the job done. Which inequalities are we going to be talking about? Well, I'll tell you. We're going to be talking about Markov, Chebyshev, Chernoff, Jensen, Hölder, and Minkowski's inequality. All very good things, all very useful tools. But stay tuned to the end of this lecture because we'll also be talking about how to approximate LP functions by simple functions, which, yeah, sure, we did that for measurable functions, right? But this is going to be a fun proof because it's going to allow us to use 1, inequalities from LP spaces, 2, Dynkin pi lambda, and 3, dominated convergence, one of our favorite convergence theorems. So put this all together and it turns out that yes, you can in fact approximate a simple or a LP function by a simple function. But can you prove it? Let's go check out the notes and show how it's done. Am I standing in a creek bed? Welcome back to another lecture of probability and measure. Today what we'll be talking about are LP spaces. In some sense, this lecture and the next lecture, which will be on convergence of measure, are all gearing up for two things. One is to prove the law of large numbers, and the second is to prove the ergodic theorem, which is in some sense like a more powerful general version of the law of large numbers. But to get there, we need some preliminary work. We need some nice little tools, some inequalities. We need some power. And specifically today, we'll be talking about LP spaces. This allows us to, well, LP spaces, right, or what? They're Banach spaces, if you like Banach space, if you know what that is, right? Complete normed linear spaces. And they're going to show up a lot in the context of probability and measure, specifically because in some sense, an LP norm is really a pth moment of a random variable. So that's going to allow us to do lots of interesting things with respect to like thinking about variances, for example, as like an L2 norm. Nevertheless, why ramble about it? Let's just get into the notes and look at all these results. All right, so today's lecture is going to be on LP spaces, as I mentioned. Now, again, what does that exactly mean? Well, let's define this first. We, in some sense, already saw this in the sense that we talked about integrable functions. That's kind of the L1 setting, but we can go a little bit further. So we're going to define an LP space. So what do we need? Well, as usual, let omega f mu be a measure space. Always a good start, right? And we need some function f, measurable function, of course, mapping from omega into the extended real line. That means we include plus and minus infinity for convenience sake. F measurable, of course. Right, then we say that F is in LP of omega F mu for, in this case, P, well, 1 less than or equal to P, less than, strictly less than infinity, and we'll deal with the infinity case in a sec, if the integral over all of omega, that is, of the absolute value of f to the p is finite. Oh, d mu, of course. D mu is finite. And for p equal to infinity, what we say is that f is in L infinity omega f mu if what if the inf of, oh yes, I was looking at this thinking, what in the world did I write there? If the smallest, the inf of t in the extended real line minus infinity to infinity, such that f is less than or equal to t mu almost everywhere is finite. I'll talk about this in a second when we look at this a little bit closer, but roughly what this is kind of saying we want the smallest t such that the function f lies below t almost everywhere. So we're allowed to, let's say, blow up or go to infinity on a set of measure 0, as long as as long as, I guess, off of that set of measure 0, we have this boundedness condition. This is the L infinity or the L infinity setting, and we'll talk about this as it is a norm, but we'll talk about that in 1 second. So what is an LP space? An LP space is a space of measurable functions, but measurable functions that satisfy some integrability condition. In this case, LP means, well, we can integrate the f to the pth power with the absolute value to deal with all the headaches, of course, of negative signs, which are just the worst in this course, right? But the LP space while it's a space of functions, it's also a normed space. As I mentioned in the beginning, it's a Banach space, which means it's a complete linear normed linear space. I'm not going to prove that because I don't really feel like it, but you can prove the completeness of the space, right? And yeah, and then of course norms we're going to write down right now. So we'll say LP spaces are normed spaces. I guess what I'm going to do is I'm going to write something down. We won't know a priori that it's a norm. I'm telling you it's a norm, but we won't know it's a norm until we check the conditions of it being a norm, which is actually one of the results we're going to prove, called Minkowski's inequality. But at this point, you can kind of take for granted that it's a norm, and then we'll actually prove it a little bit later. In this case, we define the LP norm for p finite to be the integral of the absolute value of f to the p d mu, and that's all to the 1 over p. And this is for 1 less than or equal to p less than infinity. If p is less than 1, I always forget if it's a semi-norm or a quasi-norm, but basically the triangle inequality fails. So you can still define this thing if p is less than 1, but then you no longer have a proper norm. The ball that you get from the norm it's no longer convex, which is a problem. Nevertheless, we can also define the L infinity norm, which is exactly what I wrote up above, but I'll write it in a couple different ways just to, I'll copy what I have above, and then I'll write it in a slightly different way. So again, it's the smallest value of t such that f lies below t, mu almost everywhere. And this is also can be thought of as the smallest t in minus infinity, the extended real line here, such that the measure, just to be like explicitly clear what I mean by saying mu almost everywhere, because sometimes you kind of forget, right, what this means. It means if I consider the set of all omega such that f is greater than t, then this is going to have mu measure 0. And sometimes, not to like confuse the infant soup notation, you'll see someone write S soup, I guess of f, of absolute value of f, which stands for essential supremum. So again, it's the supremum up to a set of measure 0. So just to draw a picture, because in case it's not like clear, right? You could have something that looks like a function that looks like this with a hole taken out of it and some point up here. So this guy up here is the, you're not going to see this because I'm going to be overlaying it with my video. The soup is this point up here, but the essential soup, again, we're assuming, I guess, Lebesgue measure or something, so that the individual point has measure 0, and we don't have any like point masses. But the essential supremum is going to be the top of this parabola that I drew. So that's the difference, right? On a set of measure 0, we can get a little bit higher in the soup, but we don't care about that. We just care about it almost everywhere. And hence why it's defined as an inf, right? It's the smallest t that this holds. So you can, in some sense, make the measure 0 set as big as possible, if it makes sense to make it as big, since it's still measure 0. Nevertheless, that's the norms that we have. Again, a priori, we don't know that they're norms. So what's a norm, right? A norm is going to be a function taking one of our, well, elements of our space, in this case an f, and mapping it into the positive or non-negative reals. We want 0 to be 0. That's true. We also need the triangle inequality. I guess we need it to be positive homogeneous, which should be obvious because if you multiply one of these f's by a scalar multiple, well, it just factors out. That's easy. The hard part, the triangle inequality, right? We need to show that. That's going to be Minkowski's inequality a little bit later in this lecture to show that this is actually a norm. Anyway, we also have one more definition, which is conjugate pairs. So we say that for 1 less than, strictly less than, p, q less than infinity, we say p and q are conjugate pairs if 1 over p plus 1 over q is equal to 1. When you first see it, it's like, okay, why? Well, it's going to be really important when we do Hölder's inequality in a second. A priori, it doesn't really make sense why we're defining it that way, but it actually is just a very beautiful relation that's going to relate an LP space to an LQ space if P and Q are conjugate pairs. So it's very nice the way it works out in practice. But yeah, when you first see it, if this is you seeing it for the first time, you're probably thinking, why in the world are we defining this? But it's going to be important. Trust me, very, very important. Also, 1 and infinity are conjugates. Don't really want to write 1 divided by infinity, but if we're okay with hand waving past that, then if you say 1 divided by infinity, you get 0. So we'll just take it like that. Anyway, yeah. In what follows, f and g are all going to be measurable functions. I'm not going to keep writing it because it's always going to be measurable functions. Omega f mu is a measure space, etc., etc. If anything specifically needs to be mentioned, I will mention it. Otherwise, I'm just not going to bother repeating that every single time. Okay, so now the rest of this lecture is basically about inequality. But the good kind, right? Like Markov and Chernoff's inequality, which is the first one we're going to be doing. Oh, Markov, Chebyshev, Chernoff. There's all these names that get associated with this. Markov slash Chebyshev with, I guess, the closest English letter approximation to Chebyshev. And Chernoff. And Jensen's inequality. These are 2 different things we're going to be talking about. The first one we're going to need is the Markov's inequality. This is a very useful result. You may have seen it if you've ever taken a probability course. Even a non-measure theoretic probability course will often introduce Markov's inequality because it's super useful. It's almost more useful in the Chebyshev form, which we'll talk about in a second. We use that to prove the weak law of large numbers. But first, we'll just have general Markov's inequality. So what's Markov's inequality say if we use it, especially in our measure theoretic context? Well, it says let f be a non-negative. Non-negative is an important bit here. Measurable function. And we need t to be greater than 0, some t greater than 0. Then, well, we're going to denote that f, this is shorthand, right? If we have the set f greater than t, what do we mean? Well, strictly speaking, we're defining that to be all of the omega in omega such that f omega is greater than t. So when I write the set f greater than t, I'm talking about a set, a subset of omega, an element of our sigma field. F is measurable, so it has to be an element of our sigma field. So this is a measurable set in the language of probability and measure. Anyway, given that, the conclusion is that the mu measure of f greater than t is going to be less than or equal to 1 over t times the integral of f d mu. So this, we'll give it a little box because this is kind of the main Markov inequality here. Okay, how do we prove that? Well, we can prove that in like one line. The proof is basically that note that t, which in this case we think of t as some fixed constant, right? We can play with it, right, if we're using Markov's inequality to prove something, but right now we can just think t is just any positive number, but fixed. And if we consider the indicator function f greater than t, well, this thing is going to be less than or equal to f. I mean, I can draw a picture to explain what's going on here, right? If we think about some function f, which might kind of move around in weird ways, and we have some value t, then what we're basically doing is we're creating some indicator function for t, which is going to look like the blue line here, and f is going to be the green line, and what we're saying is, well, f is greater than t times this indicator function, which, yeah, okay, that sort of just makes sense. Again, it doesn't have to be a nice continuous function like I drew here, but it's just easy for the visualization. Then, by monotonicity of the integral, i.e. if I have two positive functions, one is bigger than the other, then the integral of the first one is going to be less than the integral of the second one, the bigger one. Then what we get is that t times the measure of our set f greater than t is going to be, well, equal to, if we think about what this is as an integral, not as a measure of a set, but as an integral of a function, this is t times the integral of the indicator function of f greater than t, d mu. And by monotonicity, this thing is less than or equal to the integral of f d mu. And then we're done because we divide both sides by t. And thus we have done it, right? Divide by t, and we're done. That's Markov's inequality. Like I said, one-line proof, but I think it still deserves a nice little QED box. Now, there are lots of ways you can use this. So like on the surface, it's like, okay, great. Is that really that useful? Well, yeah, it actually is. But it's useful in two special ways that you may see a lot in practice. So useful ways to use Markov's inequality. The first is often given the name Chebyshev's inequality. And what Chebyshev's inequality says is that for f measurable, not necessarily positive, non-negative, that is. It could just be any measurable f. And some value eta, I think that's eta, I always get the Greek letters backwards, eta in R, what we get is that the measure of the set f, that's not what I want. We want the measure of the set of f. Oh, no, eta wasn't supposed to be in. Eta's for the next one. I want m. M for mean. It doesn't have to necessarily be mean. It just could be any number in R, but typically it's going to be the mean when we talk about a probability, random variables and probability measures. But anyway, f measurable, m is some number. If we consider f minus m in absolute value and ask, well, for the set of omega such that that is greater than t, then the measure of that set is going to be less than t to the minus 2 integral of f minus m squared d mu. And the reason why this is really useful, because this shows that we can bound a tail probability by the variance of that random variable. Specifically, what we are actually doing here is we're saying the probability that some random variable x minus its mean being greater than t is less than or equal to the variance of x divided by t squared. So this is a tail probability, and this is a inverse quadratic. The variance is constant in this case, right? X is just x. So what it's saying is that if I have a random variable x, it's going to, in some sense, the tails will decay as we move away from the origin. Again, real valued random variable. And what Chebyshev says is that, well, as we move away from the mean, the tail is going to be bounded above by the probability of the tails is going to be bounded above by, well, the variance divided by t squared. So as t gets big, as we move away from the mean, the tails get the probability held in the tails goes to 0. This only works if you have a finite variance, but, well, a lot of times we have a finite variance. And as you will see in 2 lectures from now, when we prove the strong law of large numbers, even if you don't have a finite variance, sometimes you can force a finite variance. We'll see what happens, but that's 2 lectures from now. Anyway, the point is, this is super useful. Definitely, be aware of that. Another one of my all-time favorite extensions of Markov's inequality is Chernoff's inequality. This is the one where eta comes in. Usually I use lambda in this case, but the problem is lambda is Lebesgue measure in this course, so we're using eta. Anyway, Chernoff's inequality says for f measurable, and eta in R, then the measure mu of f being greater than t is bounded above by e to the minus eta t times the integral of e to the eta f d mu. Now, this one's pretty cool because what we're doing is we're basically bounding a tail probability using the Laplace transform. Now, the Laplace transform, this e to the integral of e eta f, is the moment generating function from probability theory. So this is basically a moment generating function. Super useful in the context of concentration of measure if you're, well, into that sort of thing. Anyway, I really like that result. We're not going to use Chernoff's inequality in this course. We're going to use Chebyshev a lot. We're not using Chernoff, I don't think, but I still like to introduce it because it's a really cool result. It's pretty simple. You're just applying Markov's inequality to e to the eta f. But still, you can use it to get some really cool, powerful results out. Anyway, that's Markov's inequality and the derivatives of it. Not the literal derivatives, but derivative results of Markov's inequality. Gotta watch my language there. Next, we're going to do Jensen's inequality, an extremely useful result, but it deals with something called convex function, so we have to define what a convex function is first. So definition, convex function on R. If you really want to go down the rabbit hole, read that book by Rockefeller, which is a real pain. It's kind of like just a punch to the face if you try to read that book. It's so hard, but we're going to deal with much simpler setting for convex functions, and we're going to keep them real valued. Not going to try to be too painful well, things are painful enough dealing with measure theory, so let's not go crazy into complex numbers. Anyway, if I have an I, a subset of R, an interval, B, let's do an English sentence here. Let I, a subset of R, be an interval. Then a function, wow, I cannot spell today. And I can't even hold a pen, wow. A function, phi, mapping I, our interval, into the reals, is convex if, for all, t in 0 to 1, inclusive, and all x and y in my interval I, we have the following relation holds true, which is phi of tx plus 1 minus ty is less than or equal to t phi x plus 1 minus t phi y. Okay, so again, if you're seeing convex function definition for the first time, it might be a little confusing. What's going on here? What's going on here is that if we have some function, let's draw it in blue, that's going to be my convex function. Maybe this is my interval. It doesn't really matter. Interval could be all of R, so I don't really care. Let's pick an x and a y. Well, the left-hand side of this inequality is doing some kind of convex combination. So I'm picking a point in between x and y, and I'm getting its value of phi. That's the left-hand side. The right-hand side, let's change the color so it's not all red. The right-hand side says I need to effectively draw a line in between the point x and y on the graph of phi, and I get something that's bigger than it. So this is the right-hand side of the equation of the inequality, and this guy is the left-hand side. It means that the secant line is going to lie above the plot of the graph. And of course, you can define this more generally. We're not going to. We're going to just deal with this for now. But yeah, convex function, super useful. good to know that definition. Okay, well, now that we have the definition of a convex function, we can define, or we can state and prove Jensen's inequality. Jensen's inequality. I don't actually know who Jensen is. I don't know who any of these mathematicians are. I really need to take a math history course. I always wonder sometimes who these people are and their names associated with things. Anyway, Jensen's inequality, super useful. And it says, in the measure theory context, let omega f p, that's right, we're going to deal with p, be a probability space. And x, an integrable random variable and actually if we want to use our notation, i.e. x is in L1 omega f p. Yeah, so we already have shorthand notation for that, but it's always good to write it out so we make sure that you know what in the world I'm talking about. Anyway, okay, so we have our probability space, x is an integrable random variable, such that x is going to map from omega into our interval I, which is a subset, or possibly the entire real line, in interval. Then, for any convex function phi, I wasn't using the bold capital phi, mapping from I into the reals, we have that phi of the integral of x d mu is going to be bounded above by the integral of phi x d mu. So what did we do? We swapped the order of phi and integration, right? And it's always a good day when you can figure out how to swap integrals with other things. If we want to write this in shorthand notation using the expected value as the integral, what we're basically saying is phi of the expected value of x is less than or equal to the expected value of phi of x. If we think of expectation as, right, the mean of the random variable, then we're basically saying the mean of this transformed random variable is going to be no smaller than phi of the mean. Again, very, very useful result. And the proof isn't too long, so let's prove it. All right, so we'll start with for some c in our interval I, if x is just equal to c, we'll say p almost everywhere. So this means if x is almost everywhere constant, well, then we're done and it's super boring. Then we're done. Why are we done? Well, you can just plug in c and you find out that phi of c is, well, less than or equal to phi of c. Not very interesting. I guess the only interesting bit is that it doesn't have to be strictly constant, but just constant almost everywhere. So as often in measure theory, you're allowed to mess things up on a set of measure 0. Doesn't change anything. Let's do something more interesting. Otherwise, else let m be the mean, the expected value of x, which is in the interior of I. This is why we take out the constant bit as a separate case, right? Because x, right, it's starting from omega, and it's, I guess, codomain, right, is I, the interval. Well, if x is just constant, then effectively I is just going to be the point C, which means we don't really have an interval now. We just have a singular point, and we can't have a convex function if we only have one single point where we're defining it. We need at least, I wonder how many points we need. I guess we need 2 points to make a line. 3 points, right? So you have something below the secant line. Nevertheless, we want an interval, and we want the mean of x to lie within that interval, in the interior of it. And all that means is that, for any epsilon, or not for any epsilon, there exists an epsilon such that I can draw a little ball, an epsilon ball around M, and it lies within I. Maybe I'll write that out just to be extra explicit. i.e., there exists an epsilon greater than 0 such that M minus epsilon, M plus epsilon is a subset of I. I guess it could be the whole thing, but who cares? The point is that it's contained within I. So we can take a little tiny neighborhood of M, it's in I, M is in the interior. That's going to be important because we need points on the left and we need points on the right to make this work. Anyway, yeah, we're going to choose some, yeah. So then we can choose an A and a B in R such that phi of x is greater than or equal to ax plus b, and this is for all x in the interval I. And not done yet. And phi of m is equal to a m plus b. So what are we doing? We're finding the point where the mean is. Think of this as a function, and m is just a point. We're finding that point, and we're drawing a line such that that line is underneath phi and touches phi at a single point. Well, it could touch phi at more than one point, but it at least touches phi at the point phi of m. It doesn't have to be strictly convex, but so you could have more than one point. But it's something that's going to look roughly like this. I like my little pictures, right? Here's m. It's probably not right, but whatever. The point is I can choose a point m. It lies inside my interval, and I can draw a line that just touches my function at m. And again, it actually could touch the function at other places. The important thing is that it touches it at m. And I think I put a footnote. Yeah, this is a property of a convex function. Try to show it yourself, which is my way of saying I'm too lazy to write out all the details. But yeah, you can imagine that. Yeah, that's probably true. Then what we get is that phi of x is going to be greater than or equal to ax plus b. Of course, remember, if we forget about x as being a random variable, just think of x as a measurable function. I put in an omega, I get out a point in the interval I, and that means that for any omega, I'm going to get a point in the interval I, and we set up phi and a and b in such a way that this is going to hold true. So you don't have to think about this as a random variable, but as a just some value, any value in the interval I. Therefore, phi of the expected value of x is just going to equal a m plus b by the way that we chose a and b. This is going to equal, well, the expected value of ax plus b because, I guess, expected values are integrals, and integrals are linear, so yeah, we can do that. And by just applying this thing up here, we have that this is less than or equal to the expected value of phi x. And we're basically done. We're not 100% done. That's what we wanted to show. We just got to make sure it makes sense. So the point is, lastly, is the expected value of, wait, which way are we going here? Yeah, expected value of phi of x well defined, i.e., not equal to infinity minus infinity, which is going to give you a headache, right? We don't want it. Phi could be, well, it could be positive, it could be negative, it could be both. So a priori, are we sure that we can take an expected value of phi of x, right? We don't know that. We can, but we need to check that, right? We need to make sure it makes sense. So to do that, write phi, as usual, as its positive bit minus its negative bit, where phi plus and phi minus are both non-negative functions. Here, phi minus is concave. Mainly, it's a convex function times minus 1, hence concave. And we have another result, which is phi, not phi inverse, sorry, phi minus the negative piece, x, is going to be less than or equal to absolute A, absolute x, plus absolute B. If you believe that, let's draw another picture, right? You can try to prove these things more rigorously, but I find the pictures are generally sufficient just to give you some intuition as to what's going on. So if I have my convex function here, then I take the negative bit and I kind of flip it over, and the negative bit is going to look like this. So red is going to be my phi minus, right? And what this is telling us here is that if I have my, well, I guess if I have something like this, my line, ax plus b, that lies below it, then if I kind of absolute value everything, do I want an absolute value on the x? Maybe I do. I think no, of course, yeah, because we don't want it to be negative. Yeah, that would be bad. That would be bad. Yeah, we get another line that's like up here. So basically what we're saying is if phi lies above this line, then phi minus is going to be a concave function which lies below some mirrored image of this line, for lack of a better way of writing it. Anyway, oh wait, but it's absolute value of b. So this actually is probably not going to be touching it. It's probably going to be a lot higher. Because in this case, b would be the intercept. So I'm going to redraw that. It's actually probably just a line up here. The point is, it doesn't actually have to be sharp in the sense that it doesn't have to touch my red curve. It just has to be above the red curve. And the reason for that is for this last line, which is hence the expected value of phi of x is going to be bounded above by a expected value of absolute x plus absolute b, and we know this is finite. Why do we know this is finite? We know it's finite because x is integrable, right? X is L1, it's integrable. And now we can conclude. And it's good to point that out, because if you didn't do that check, you might go through this whole thing and think, well, wait, we didn't even use the fact that x is integrable. The condition up here that x be integrable, this one, right? This is important because otherwise the right-hand side might not make any sense. And that's important, right? We need to make sure that this actually, well, if we're going to have an inequality, we have to make sure that this actually makes sense. The right-hand side here makes sense. We can integrate phi of x. The reason why we can integrate phi of x or take its expected value is because x itself is integrable. Otherwise, we can get ourselves into big trouble. So, subtlety, but very important to be aware of, right? Cool, so that's kind of like part one. Part two we're going to do now is Hölder and Minkowski's inequality. Hölder with the umlaut, I think that's an umlaut, right? The two dots, I forget. The two dots above the O, and Minkowski. These are also super useful results. I feel like I'm making one of those YouTube list videos, like, let's talk about everyone's favorite top 10 inequalities. I bet somebody's done that before. There's a bunch of so many random videos out there. If not, maybe we can do one just for fun when I have time. More as a mockery of YouTube list videos, but that would be kind of fun to do anyway. Anyway, Hölder's inequality. Let P and Q be in 1 to infinity inclusive conjugate pairs. We'll say pairs. As we talked about at the beginning, we need F and G are measurable. Okay, let omega F mu be a measure space, etc., etc. Don't really care. The point is we have two measurable functions. Then the L1 norm, the integral, the absolute integral of F times G is going to be bounded above by norm F, P norm of F, and the Q norm of G. Actually, yeah, I was going to say, assuming they exist, but they don't even have to exist because the right-hand side would be infinity, still holds true. Let's prove it. So, if either... First, we got to like sweep under the rug all the dumb possibilities, which is if either, well, the P norm of F is 0, or infinity, or G, Q, not the magazine, is 0 or infinity, then we're done. So, of course, if one of these is equal to infinity, the right-hand side is infinity, everything has to be positive, so certainly this inequality would hold. I guess, on the other hand, if one of these is equal to 0... Oh yeah, it's a norm, of course. So if it's equal to 0, the question would be, well, does that imply the left-hand side is also 0? It does, because if the LP norm of F is 0, then that implies that F is 0 almost everywhere, and thus F times G would be 0 almost everywhere, and thus everything would just be 0. It is good just to think through it for a second, but yeah. That one we're done with. Hence, let 0 be strictly less than the norm, the P norm of F be strictly less than infinity, so we have something interesting we can work with. Then we can normalize and say, without loss of generality, we're just going to assume this is equal to 1. It's some positive number, so we can divide everything by that value and just assume it's equal to 1. Make our life a little bit easier so we don't have to drag that around. Thus, we can define a probability measure. Again, we're starting just with mu as some measure in some measure space. We can define a probability measure P so that P of A is going to be defined as the integral over A of f d mu. Because of the normalization, that means that P of omega is going to equal 1. Therefore, we have a probability measure. It's kind of neat because Hölder's inequality doesn't strictly require probability, but we're going to use a probability measure to get it. And we're going to use Jensen's inequality. Then, via Jensen, which we just proved a second ago, and noting that Q times 1 minus P is equal to P. This is the conjugate pair trickiness, right? So because of 1 over Q plus 1 over P is equal to 1, you can rearrange the terms to get that crazy looking thing. But that's actually going to be, oh, no, wait. P minus 1. Typo. And do we have to consider the case where P is equal to 1 and Q is equal to infinity separately? We probably have to consider that separately. Let's just assume for now that P and Q are strictly between 1 and infinity, and then we can... Oh, I guess the other cases are kind of dumb, right? Because if one of them's infinity, you're just taking a max, and you can always just pull the max out of the integral, and then you're done. Okay, yeah, so I guess the P and Q equal to infinity is not interesting. Here we'll assume 1 less than P, Q less than infinity conjugates. Otherwise, yeah. Anyway, after this, we're just going to solve the problem, which is the norm of fg in L1 is, by definition, going to be the integral of the absolute value of f times g d mu. This thing can be rewritten as g divided by f the p minus 1 indicator function that this thing is not 0 because we don't want it to be 0. We're going to have a bad time. D mu. Of course, if it's 0, we're just adding, like, if f is 0 for any significant piece of omega, then it's just going to be a 0 in our integral. So it's not going to add anything, so we don't particularly care. We can just ignore the bits where f is 0 and just consider the points where f, that is the absolute value of f, is greater than 0. So all I did there was, in some sense, multiply and divide by f to the p minus 1. And then with the little indicator function to make sure we don't have anything that's ill-defined. Anyway, what we get from there is a little bit more interesting, which is that this, via Jensen's inequality, right, is going to be the integral of GQ divided by FQ P minus 1 indicator function F absolute F greater than 0 F to the P, because this is a probability measure d mu, right? Something like this. Okay, why in the world is that true? If we think of this, what we're really doing is we are... How do we want to do this? Let's see. Well, I'm going to write the conclusion, and then I'm going to go back and justify why that's true using Jensen's inequality. The conclusion now is simply to, well, simplify things. Use the fact that Q times P minus 1 is equal to P. Cancel all the F's out, and what you're left with is just the integral of G to the Q dq 1 over q. And this is precisely fp, which we, without loss of generality, set equal to 1. So I can just bring it back in from nowhere, ngq. And that's the conclusion. But I think it's worth talking about what in the world is going on in that line. So let's look at that in a little bit more detail, just to make sure it's clear to everyone, right? What we're doing, what is phi, right? Phi is our convex function, and Jensen said if we take a convex function and put it inside an integral, the thing gets bigger. Let's try and do that. In this case, phi, what are we putting inside the integral? We're putting phi of x is going to be x to the q. Q has to be greater than 1, therefore this is a convex function. So what we're really doing is we're writing here that the integral, well, what we're saying is we're saying phi of, sorry about the crazy brackets, phi of this thing, indicator f greater than 0, f p d mu. That's this line up here. Right, all I did was say take it to the qth power, and then take it to the 1 over qth power. The q's would cancel out. But most importantly, this is a prob measure, as noted above. And this is convex, which means we can pop it inside and make the whole thing bigger. So this is less than or equal to, oh, I switched colors. This is less than or equal to, right, the integral of phi applied to this function, indicator f greater than 0, integrated with respect to the probability measure. Because, right, when you first look at this, you might think, well, why didn't I take f to the p to the qth power? That's not part of the function. That's the probability measure, right? So there's two things going on here. That's what we're doing. So hopefully that's clear. If not, try to stare at it a little bit. Jensen's inequality is super useful, again, because you can move powers like, you know, q, like the whatever q is, from between 1 and infinity, you can move it in and out of the integral. And of course get an inequality, but in this case we're good. We've proved what we needed to prove. Oh yes, and note, for p equal to q equal to 2, we have the famous Cauchy-Schwarz inequality. Schwarz spelled with no T, as the professor that I took this from years ago would always remind us. Don't put a T in Schwarz. It's just Cauchy-Schwarz. Anyway, yeah, Cauchy-Schwarz, super useful. It's a specific case of Hölder's inequality, but it also does apply if you like inner products. I'm not really going to get into Hilbert spaces in these lecture notes, but right, L2 is a Hilbert space, so we can think of this as like an inequality between the inner product in the L2 inner product and the norms, the L2 norms. But I'm not going to worry about that too much right now, because I really want to get to more of the convergence of probability stuff. And we still need to get through Minkowski's inequality and an approximation theorem before we're done with today's lecture. All right, Minkowski's inequality. This one is basically telling us, yes, that LP norm is actually a norm because it satisfies subadditivity. So let P be in 1 to infinity, and F and G measurable. Then, simply put, the norm of F plus G, the LP norm, is less than or equal to the LP norm of F, or the LP norm of F plus the LP norm of G. This is subadditivity of this thing. I guess with a P or a Q. Doesn't really matter. It's all notation. Right, so this is important because a priori we don't know that this thing is subadditive. We don't know that it's a norm. Turns out it is, but we got to prove it. So let's do that. And we're going to use Hölder's inequality, which is why we're presenting it in this way, right? Jensen, we used to prove Hölder. Hölder, we used to prove Minkowski. And then, we're going to run over time, but there's a fun little theorem about approximation in LP spaces that I want to do anyway, so we're going to do it. Let's prove this first. First, if we're going to do all the dumb cases, the trivial cases, sorry, the dumb cases. If FP is equal to infinity or GP is equal to infinity, then we're done. Because the left-hand side is, or the right-hand side is infinity, it doesn't matter what the right-hand side is, or the left-hand side is, because it has to be greater than 0 and less than or greater than or equal to 0, less than or equal to infinity. That's the first silly trivial case. If F plus G is equal to 0, then that means that F plus G is now going to be, well, equal to 0 with mu almost everywhere. So we're done because, well, the right-hand side has to be greater than or equal to 0. So that's not interesting. And lastly, for the trivial cases, if P is equal to 1, then use the fact that the absolute value of F plus G of omega is less than or equal to F of omega plus G of omega, and done. Because, of course, integrals are linear, so we can just integrate both sides of that, and we get the result we want. Now, the other cases are where things are going to get a little bit trickier. So now, otherwise, what do? Well, what we do is we take F plus G, the P, and we write it in kind of a special way. What we do is we multiply by 2 and divide by 2. So we get 2 to the P, F plus G divided by 2 to the P. Cool. So I multiplied and divided by 2 to the P. But now what we can do is we can use a little convexity trick, right? Because in some sense, this is a convex combination. I'm averaging F and G together, if you like, or adding them to each other. We can use a little convexity trick to show that this is less than or equal to 2 to the P times 1/2 absolute F to the P plus 1/2 absolute G to the P. This is a convex function. And this thing is equal to 2 to the P minus 1 FP, F to the P, plus F to the, or G to the P. Great, so what does that mean? Well, therefore, the integral of the absolute value of F plus G to the Pth power, the thing that we're interested in, right, is going to be less than or equal to 2 to the P minus 1 integral of f p d mu plus 2 to the p minus 1 integral f g to the p d mu. What does that tell us? Well, that says that this thing has to be finite. Oh yes, because I was going to say, we didn't assume that f and g are LP functions, but we kind of did in this part of the proof, because we already assumed that they have finite norms. So if the norm of if the p norm of f is finite and the p norm of g is finite, then what we're showing is that this f plus g is going to be an LP, I guess, omega f mu, which is to say that it makes sense, right? That we can write down the integral of f plus g. And if f and g both have finite norms, then f plus g is going to have a finite norm. So that's good. Again, that first bit is just to make sure that everything makes sense. Now, assuming that f plus g, p, is strictly greater than 0, otherwise we're done, as I mentioned, kind of one of the trivial cases, and p is greater than 1, and p and q are conjugates, then, see, Hölder's inequality is coming back, hence the conjugates bit. Then, now this is kind of neat, what we have is that the norm of f plus the q norm now, of the absolute value of f plus g to the p minus 1 q norm is equal to the integral of f plus g to the p minus 1 times q, that same looking weird thing from above, right? All to the 1 over q. Well, we know what that is. This is just the integral of f plus g p to the p d mu 1 over q. And actually, furthermore, we can write 1 over q in a special way, which is p minus 1 over p. And if we write it like that, what we see here is that we actually have the norm of f plus g in LP, but to the p minus 1 power. So what did we do? We changed a q norm into a p norm. Why is that useful? Well, it's going to be useful because we can use that to finish the proof. Therefore, if we start with what we're actually interested in, which is f plus g p p, then this is going to be the integral of f plus g the p d mu. Okay, well, that's just by definition. Now we can make this thing less than or equal to by using, let me write it out first. Basically, what we can do is we can pull out one of the f plus g's, break up the absolute value of f plus g into absolute f plus absolute g, and we get something like this. Absolute f, and what's remaining here is going to be a p minus 1 d mu, and absolute g, f plus g, p minus 1 d mu. Okay, where are we going from that? Well, now what we can do is we can kind of, well, we can hit it with Hölder's inequality. Yeah, this is where we want that, right? Up above up above we didn't use, we just kind of manipulated the terms. Now what we're going to do is we're going to hit this with Hölder's inequality, because what we have is we have the norm, or we have the L1 norm of f and f plus g to the p minus 1. So what we can do is we can rewrite this as f in P norm and F plus G to the P minus 1 in Q norm. Yes. And the same thing for the second term, but with G instead of F. I think that looks good. Cool. Now we can use that little derivation that we did up above to switch Q norm back to P norm. And it turns out that this thing is F P, F plus G, P, P minus 1, G, P, F plus G to the P minus 1. All right. Divide everything by F plus G to the P minus 1, and we're done. So we divide this by F plus G, P minus 1. We divide the thing we started with by F plus G, P minus 1, P norm. And that's it. We just proved Minkowski's inequality. Switch back to black and QED. Okay. So that's more or less all the results that I really wanted to cover in today's lecture, but there is one really cool theorem that I thought it would be fun to do, which would show an example of what we can do with, well, spaces of LP functions, which is we can approximate other things, right? This is very similar to, so let's step back for a second. If you recall when we talked about measurable functions, what did we do? Well, we started with indicator functions. We created simple functions, and we can use those simple functions to build up to measurable functions. We can do very similar things in LP spaces, and that's what we're going to talk about in the final theorem of today's lecture, which we will call approximation in LP space. That L looks kind of like a parenthesis. There we go. Okay, so let's do some approximation. What's the theorem say? As usual, let omega f mu be a measure space. I always like to make sure that I'm not supposed to say sigma finite. Not in this case, but it always is good to double check. We have a measure space, and we have A is a pi system. Oh goody, right? Our good friend the pi system from the Dynkin pi lambda theorem is back. We have a condition. This is a pi system such that sigma of A is equal to F. So we have a pi system that generates the sigma field we're working in. So for example, we could have the real line for omega, we could have the Borel sets, I guess, for F, and A could just be all the half-open intervals, right? The pi system says I can intersect two things, and I'm still in the pi system. If I take two half-open intervals, I intersect them, I still have a half-open interval. And if we sigmify the half-open intervals, we get the Borel sets. So that would be like a very standard example of where you can use this, but you can go a little bit further. Oh yeah, and we're not actually done yet. And the measure of A has to be finite for all A in A. Yeah, I guess and we're almost there. And there exists AI in A such that AI increases to omega. Okay, now we're there because, okay, we could take bounded half-opened intervals and we can expand those until they take up the entire real line, right? They're still going to have finite measures, each of them, but eventually they'll take up the entire real line. It actually is kind of interesting. It makes me wonder if, given these conditions, you necessarily will have to have a sigma finite measure, because you're effectively approximating omega by an increasing sequence of sets that have finite measures. I'm not sure. Maybe there's some weird, strange subtleties where there's like some dumb things you can do where you can have like everything be finite but set the measure of omega to be infinite or something. But I think we can leave that speculation for another day. Anyway, we're not even to like the conclusion of the theorem. We have another let V not. It's going to be a linear space of simple functions, but be the sum I from 1 to n of AI indicator AI such that AI is real, capital AI is an element of script A, if we don't have enough A's already, and n is some natural number. Simple functions. But simple functions on the pi system A, whereas before we could take simple functions where the sets could be any measurable set, any set in the sigma field. Here, we're just taking simple functions where their sets are made up of elements of A. So subtle difference there, but important. It's a simpler collection of simple functions. For P in 1 to infinity, but not including infinity, because I think weird and bad things happen in infinity. I forgot to write that down in my notes, but I'm pretty sure bad things happen in L infinity, because it's not... I think L infinity isn't separable, but I had to double check that. I always had to double check these definitions. Anyway, for P in this, for P some value between 1 and infinity, then what we have is that our functions here are a subset of LP. That seems kind of obvious, but, and more interestingly, for all F in LP, and for all epsilon greater than 0, there exists a V in V naught, such that the norm of F minus V, the P norm, is less than epsilon. Now that's kind of cool, because what that says is that I don't even need the entire sigma field, I just need a pi system that generates it. And I can get a simple function on my pi system that can be arbitrarily close in an LP sense to any LP function F. That's kind of neat. It means that we can approximate things in LP by simple functions. Because we've in some sense changed, right, the metric or the norm that we're working in. But as I say, don't take my word for it. Let's prove it. Okay. For any A, set A in script A, the pi system, the norm of the indicator function of A, the P norm that is simply just, well, the integral of this indicator function d mu to the 1 over pth power, and that's going to be the measure of A to the 1 over p, and this is going to be finite by assumption, because again, we constructed A, the pi system, such that the measure of any set A in the pi system is going to be finite, and that's why it's important, because of that, what we have is therefore indicator functions for sets A in the pi system are LP functions. Otherwise, we'd run into some trouble. For any A. So this deals with that, so we can integrate these things. And then as LP is linear, i.e. I can add two things, I'm still in LP. I can multiply by a scalar multiple, still in LP. What that means is that as LP is linear, this entire space V naught is a subset of LP. So at the very least, we've just shown that now all of these simple functions are LP functions. That's a good starting point. Now, next, let V, a subset of LP, be all F in LP, or contain all F in LP, that can be approximated as above by some V in V naught. So obviously the goal now is we have a set V of LP functions that can be approximated. It's certainly not empty because V naught is in LP. So, okay, it makes sense to at least talk about this set. And our goal is to show that this V is a subset of LP is actually V is equal to LP. So let F in LP be approximated, in V, I think. Let F and G in V be approximated by VF and VG, respectively. Then, by Minkowski's inequality, what do we have? Well, what we have is we have that F plus G minus the approximation simple functions VF plus VG in P norm is going to be less than or equal to, well, F minus VF plus G minus VG. And VF and VG were selected so that these two things are both less than epsilon. This is less than 2 epsilon. So that's kind of cool. Therefore, V is also a linear space. The point being, if I have two functions that can be approximated in this way, I can add them together, and that function, that new function, F plus G, can also be approximated in LP. So that's good. We have a linear space. Now, so this is the first bit, and then next, assume omega is in A. This is a stronger assumption, right? We're not assuming, we didn't assume at the beginning that omega is in A, but for now, we're going to assume it. We're going to prove in this case, and then we're going to generalize beyond it to omega not in A. So just to recall that if omega is in A, what this means is that we have a finite measure. Because anything in A has to have a finite measure by assumption. So we're going to let L be the collection of sets B in, not in, that's a typo. B in omega, no. B subset of omega such that the indicator function of B is in my linear space V. And what do you think we're going to do? We're going to try to show this is a lambda system and then use Dinkin's pi lambda theorem. Okay, so what do we know about L? Well, so far we know, of course, that all of the A in the pi system A are in L, but we don't strictly know that any general set is going to be in there, and that's what we have to show. Okay, so what we have now is we have L, and what we want to do, double check. Yeah, good. I think everything's still recording. I had to switch a battery there, so I think these batteries are starting to wear out after I use them so much. Anyway, yeah. So we have that our pi system A is a subset of L. Like I said, we know that because we know that all of those indicator functions are in V for A. And therefore, by assumption, omega is also going to be in L. This is, again, because we're assuming in this part of the proof that omega is in our pi system. Now, for what we're trying to do is prove that L is actually a lambda system, right? And then we can use Dinkin pi lambda on it. Anyway, for A and B in L, such that A is contained in B, I guess like that, then our indicator function for B minus A is going to be the indicator function for B minus the indicator function for A, and this is going to be in V. Why? Because V is linear. This is a linear space. So I can subtract one thing from the other, and I'm still in the space. And lost my place. Where were we going with that? Oh, yeah. Therefore, B minus A is going to be in L. All right, so we're working our way to the lambda system. The last thing we need to do is do pairwise disjoint unions. So now we say for, maybe I should like star these things just so I see. Okay, we have this piece, we have this piece, and we have this piece to get our lambda system. For AI, I from 1 to infinity, pairwise disjoint. AI, of course, in L. What we want to show is that the union oh, that's right. I'm like, why do I have B here? What we do is we let A be the union I from 1 to infinity of AI. And we're also going to define Bj to be the union I from 1 to j of AI. So the first j of our sets, our finite union. Then the Bj's are going to increase up to set A. And furthermore, the norm of indicator A minus indicator Bj is going to be the measure of the set A minus Bj to the 1 over pth power. And this thing is going to go to 0 as j goes to infinity. Okay. Why? Well, that's because it converges, right? If Bj is going to increase to A, then we know that it also is contained within A. Then if we do this subtraction of the two indicator functions, it's just the measure of that set A minus Bj. Eventually, this convergence will happen. Whole thing goes to 0. What does that mean? That means that we can approximate. What are we doing here? This is kind of neat, right? We are approximating indicator A by indicator Bj, which means that for any epsilon greater than 0, I can find an index, I don't know, n, such that for all j greater than n, indicator Bj is going to be really close to indicator A in an LP sense. What's that mean? Therefore, A is in L. And what do we have? L is a lambda system. So all of these combine to mean that L is a lambda system. And if L is a lambda system, then Dinkin pi lambda says that F, which is equal to sigma of A, right, the sigma field generated by the pi system A, is also going to be a subset, possibly the whole thing, of the lambda system. Therefore, the indicator function B is going to be an element of our linear space V, and this is for all sets B in the sigma field F. So that's cool. So what we did, right, is what we did was we showed that, okay, V, which is all the, what was V again, right? Sometimes I forget what we're trying to show here. Let's go back and look at the definition, right? V are basically all the LP functions that work. We know that indicator for A's, A in the pi system, work. What we showed is that actually for any set B in my sigma field, indicator B is also approximatable. So that's nice. I mean, it kind of makes sense, but still it's nice. So now we want to get beyond indicator functions. For any non-negative, F in LP, we construct get all the sounds in there, construct simple functions fi. Am I using I? I'm using n, just to make sure I don't mess up the indexing. Fn, where Fn is going to be the min of two things. It's going to be the min of n, or 2 to the minus n, floor 2 to the n, f. There. So we did something very similar to this when we looked at turning simple functions into measurable functions. Now we're turning simple functions into LP functions. Such that Fn is now going to increase to f. Then, well, what happens if it increases to f? We know that in an absolute value sense, f minus fn is going to pointwise go to 0, because what we're saying is, well, fn is going to increase to f for all are we using x or omega? I kind of forget. Whatever the argument is, it's going to pointwise converge. Therefore, this difference is going to pointwise converge to 0. This is pointwise, omega f x, whatever the argument is. And furthermore, what we have is we have that f minus fn p is going to be less than or equal to just f p, right? Oh yeah, we're non-negative, so yeah, of course. F is non-negative, this thing is strictly less than f, so it's like saying, well, if we don't subtract something, it's just going to get bigger. So that makes sense. This is important. Why are we trying to bound this? We're bounding FNP. And what are we going to do that we've bounded it? We're going to apply dominated convergence. And that's why I kind of like this proof and why I wanted to include it. We get to use all the fun stuff. We get to use Minkowski. We get to use Dinkin pi lambda. We get to use dominated convergence, right? It's just a good old time. By dominated convergence, what we get is that f minus fn p, right, which is just equal, I guess I have to put the bracket around it, f minus fn p d mu. I think we were still using mu. I actually kind of forget by this point, but we'll just assume it's mu. 1 over p, right? Dominated convergence says this thing is going to go to 0 because I can move the limit from the outside to the inside, and the inside thing is going to pointwise go to 0. Therefore, the integral of the whole thing is going to go to 0. Only works if we can dominate it by something, and that's why this line is important. Therefore, f is in V. And by linearity, V is equal to LP. Are we done? We're not quite done because we assumed that omega was in our pi system. Now we have to throw that assumption out and finish the proof in full generality. Lastly, for general omega not necessarily in the pi system, I mean, could be, we showed that it works, by assumption, AI is going to increase to omega, right? We had that as our assumption before. We need that because we need it to fix this little bit. Therefore, for any f in LP, we have that f times the indicator function of AI is going to be in V, right? Because what we're basically doing is we're taking away omega and we're replacing it with an AI. With an AI. We'll all be replaced by AI someday, but in this case, we're taking omega, we're taking some set AI of finite measure, and we're replacing it with that. So that follows from this whole argument up above. But furthermore, we'll say and f minus f indicator AI in P is going to go to 0 pointwise. Because A is going to keep getting bigger, which means I'm going to recover all of my f as A is allowed to grow to omega. And pointwise, this thing's going to go to 0. So what are we going to do? Oh yeah, and this, and best run-on sentence ever, right? This is less than or equal to fp, again. Therefore, dominated convergence says f minus f indicator AI in P norm is going to go to 0. This is by dominated convergence. Therefore, f, any general measurable function, is in V. That's kind of cool. Okay, QED. Does this actually apply for non-negative f? Or, sorry, for not strictly non-negative f? If it doesn't, then I guess what we can always do is we can just say f is equal to f plus minus f minus and conclude, because show that it works for each piece. and then it works for the combination of the two pieces, each of which would be dominated in their own right. Okay, yeah, so dot dot dot, and f is equal to f plus minus f minus. I know, negative signs are just the worst thing ever. Anyway, that's what I wanted to show. I really like that proof because it combines a lot of tools that we've learned so far in this course. Minkowski's inequality, dominated convergence, Dink and pi lambda. These are three things from three different parts of the lectures that I've been talking about. They all come together, and what do they tell us? They tell us that in an LP space, we can approximate functions f by simple functions, if and actually a very special collection of simple functions that live on a pi system, assuming the pi system is nice enough that we can kind of expand it outward to cover all of omega. Cool. So that's everything I wanted to talk about today. The next lecture is going to be a fun one as well. It's on convergence in measure, convergence in probability, convergence almost surely, convergence in a weak sense, convergence in every single crazy sense. There are way too many types of convergence out there, I'll tell you right now. So get ready for that one, and I'll see you in that lecture. Look forward to it.